graph the absolute value function. Right? So we want to identify the important characteristics, most notably the A value, the H and K values, H-K values being the vertex. So from this, I mean, I'm going to probably put a little more detail here than you would need on an assessment, but just for review purposes.
I think your screen is
Frozen? Thank you. There we go. A times x minus h plus k. The A value, again, is the slope, right? But if A is positive, it opens upwards. If A is negative, it opens downwards, right? So here, A is negative. So it's going to open downward. So opens down. All right. The HK values make up the vertex. All right. So in this case, the H value is 2. The K value is also 2. All right. The absolute value of A gives you the slope, but if we look at A as the slope to the right of the vertex, that's probably the easiest way to think about it. All right. So A is the slope to the right of the vertex. So I would plot 2, 2, and then count off a slope to the right of the vertex of negative 3. All right, so that's down 3, right 1. All right, so the slope is negative 3, so down 1, 2, 3 to the right 1. Now, because there's symmetry in the absolute value function, for every point to the right, there must be a point to the left. All right, but I'll continue going to the right until I use up all the space. This would be one ray of the absolute value function. If I assume that my axis of symmetry along this dotted line, for every point to the right of that dotted line, there must also be a point to the left. All right, so that would be this point here, this point here, this point here, and this point here. And you could also look at it as saying, from the vertex, you're going to have a slope of negative 3 going to the right, also positive 3 going to the left, but I like the symmetry approach better. And that would be your absolute value graph. All right. So, like I said, the quiz is going to model this question precisely. So, you're going to see graph the following absolute value function, and then you'll be given a function. You'll notice I didn't say anything like state the vertex, state the A value, or anything like that. It's just graph the absolute value function. So if you want to do it on your calculator, by all means do so. But as I've been saying throughout the entire unit, the better approach is to do it by hand and use the calculator to check your work, because that'll be more beneficial as you go.
Can you go over how to do it on the calculator again?
Yeah, I'll do that in one shot at the end. All right. So the second one, write the equation of the absolute value function given the graph. So here we're stating the A, H, and K values. So the H and K, the vertex, negative 2, 3. Then I just need the slope going off to the right. So I'm going to pick 2 clean consecutive points, starting with the vertex going to the right. Right? Ideally starting with the vertex, but it really can be any 2 consecutive points going to the right. These 2 are pretty reasonable. So I'm looking at a slope that's down 1, right 2. So my A value is going to be negative 1/2. So again, using the same model, I'm just plugging right in. So the A value, negative 1/2, the H value is a negative 2. There's already a negative built into the equation, so negative will become positive in a sec, plus 3. So we're looking at f of x negative 1/2 x plus 2 plus 3. All right. Graphing a piecewise function, that's the one that's most involved. You're graphing, in this case, 3 pieces, so we have to deal with that, each domain, each equation. But we think of this as g of x is equal to 5x minus 3, 5x minus 3, but only when x is between 0 and negative 1. All right, so you could do this a couple of different ways. We did it using a table approach, but we also did it using just kind of a slope y-intercept, erase the parts that you don't need approach. Right? But we do have g of x equaling 5x minus 3 sometimes. Other times g of x is equal to 4. And still other times g of x is equal to negative 1/2 x plus 2. All right. If I'm using a table of values approach, then my first table is only going to span the integer values from 0 to 1. So I'd have x, I'd have g of x going from 0 to 1. So pretty small table. All right. The 0 would get an open circle. All right, because we're going to get close to 0, but we're never actually going to get there. All right, so an open circle for this point. But we plug these two values into the function, the relevant function, and that's really the end of it. We have our points and we connect them on the graph. So if I plug in a 0 for x, I get a negative 3. If I plug a 1 in for x, I get a 2. So on the graph, I'm plotting 0, negative 3, but with an open circle, and 1, 2 with a closed circle connect with a line segment. The next piece spans from 1 to 4. So you can make a table out of this, but because it's a constant function, you really don't need to, but you're welcome to. I mean, if you want a consistent approach, this method is going to work all the time. And you're probably going to need something along these lines when you get into more complicated functions, not just lines. All right. So, but this one goes from 1 to 4. All right. Still an open circle at 1. All right. That's the presence of the less than symbol. Right? But because it's a constant function, there's nowhere to substitute any of these numbers. G of x is equal to 4. That's the same as saying g of x is always equal to 4, which is the same as saying g of x is equal to 4 no matter what x is. Right? So each one of these values is going to be equal to 4. So at 1, 4, we have an open circle. 2, 4, 3, 4, 4, 4, all closed circles. Line segment connecting, if I can get it to work, do it this way. And that would be the second piece of this piecewise function. The last piece doesn't have an ending. It has a beginning, it doesn't have an ending. Starts off at positive 4, says x is greater than 4. So if I'm making a table, I could start my table at 4. I can go on to 5, to 6, to 7, and so on. Technically, I can go on to infinity. All right, but I'm not going to make a substitution for infinity. That wouldn't be practical. The 4 is going to get an open circle. I'm still going to make some substitutions, but I'm going to be strategic about this because it's a linear function. I can plug in the 4. I really don't want to plug in the 5. I'll plug in the 6. I'm going to plug in the even numbers because it's going to give me a clean result. If I plug in a 4, I get -2 plus 2 is 0. If I plug in a 5, I get a fractional value. It would be fine, but I don't want to deal with it. If I plug in the 6, I'll get a -3 plus 2 would be a -1. So I'd start off plotting those values. Since it's linear, I now know what the slope is. I mean, I already did from the equation. It was -1/2. All right. But I can now continue the trend going down 1, right 2, down 1, right 2 until I run out of room. The difference here is because I have infinity, we're going to put an arrow on the end of this graph, indicating that it goes on forever. And that would be the piecewise graph. And you'll notice there aren't any values over in the negative end of the graph here, and that's all. I mean, there could be, but that's only the nature of the domain here. The first piece has x values that are greater than 0, so it's not including 0. It's not including any negative numbers. All right. Then we have to go the other way, picking the equation off of the graph. Similar idea, except this is the one where we find the slopes, y-intercepts, or what the y-intercepts would be if you could extend the graph to the y-axis. All right. So we go to each one, count off the slope, rise over run, 2 consecutive clean points. We got 1 and 1, so the slope is 1. The y-intercept is also 1. Right? Even though it doesn't get there, the open circle, it is the location that the graph is approaching. All right. For the second piece, down 1, right 2. So down 1, right 2. The slope is equal to -1/2. Now we just got to figure out where it would go if it could get to the y-axis. It's going to be off the grid. But we now know the slope. We just trend it the opposite direction. So instead of going down 1, right 2, we'll go up 1, left 2. That's going to put us to 5. All right. The up 1 part gets us to 5 because we're at the level of 4. Getting 2 spaces over, because we're at the x value of 2, 2 spaces left will get us to 0. So the y-intercept here is 5. All right. For that last piece, we have a slope of 0. The y-intercept would be 1 if it extended to the y-axis. All right. So we have our 3 pieces. So I could write my piecewise function, f of x equals big old squiggly. The first piece, 1x plus 1. If, we'll get to the if in a minute. Second piece, -1/2 x plus 5. If. And the last piece, we could write 0x plus 1. I'm just going to write a 1, though. 0x plus 1. The 0x cancels out to 0. Plus 1 is just going to be a 1. So 1 if. Now we just need the ifs. All right, so we want to think about where this graph begins and where it ends. So the first one begins at 0 and ends at 2. So it's between 0 and 2. All right, but we have an open circle here. Open circle means less than. Closed circle on this end, less than or equal. The second piece, same deal, but this time it's going from 2 to 4. 2 to 4. All right, so 2 going to 4. open circle first, then closed circle. So less than or equal. Then the last one starts off at 4 and goes on forever. So it's starting here, and it's going to infinity. So if it could stop at infinity, if infinity was a place that you could get to, then we would say between 4 and infinity. Instead, well, we just say that x is greater than 4. Right. So pulling it from, honestly, I mean, you may disagree. I think pulling the information from the graph is easier than creating the graph, but it's just an opinion. It just seems like everything that you need is in the graph somewhere. It's just a matter of grabbing it and extracting it. Whereas when you're given the equations, it's like, all right, now where do I even start with this? So the more attention I think is probably going to be needed to be paid to number 3 than number 4. But that's just personal preference or my opinion. Number 5, square root function. Remember, the parent function is just the radical x, and everything we do based off of the transformations is going to be in relation to the radical x. So we have the vertex form, or the standard form, f of x is equal to a times the square root of x minus h plus k. The a, h's, and k's all play the same role as they did for the absolute value function. Right? A gives us a sense of the slope. H and k gives us a vertex value. Square root function is that sideways parabola chopped in half. But what I like to do is plot the square root of x first. Right? So I'm going to plot that. So 0, 0, 1, 1, 4, 2, and 9, 3. If it fits on the graph, doesn't always, but it does in this case. All right, so that's f of x is equal to the square root of x. All right, now an easy way to come up with these points so that you don't have to do it in a calculator. And again, you can do it in a calculator if you want, and I'm going to go over that in a couple minutes. Just think about what numbers are perfect squares along the x-axis. 0, yep. And what's the square root of 0? 0, so 0, 0. 1, yes. What's the square root of 1? 1, so coordinates 1, 1. 2, no. 3, no. 4, yes. What's the square root of 4? 2, so coordinates 4, 2. 5, no. 6, no. 7, no. 8, no. 9, yes. Square root of 9 is 3, so coordinates 9, 3. Next one would be 16, 4. 25, 5. So always the perfect square, comma, whatever the square root is. Right? So it's a pretty nifty way of doing it. Now, the a value is going to be -1 here. Same shape and orientation because the absolute value of -1 is 1, but it is negative, so that tells us we're going to reflect each point over the x-axis. Right. The h value is a -2. The k value is a -3. So that's telling me I'm going to shift left 2, down 3. All right. Always take care of the a values first. So if there's a reflection, stretch, shrink, take care of that first. Otherwise, you get into your shifting. All right. So if I take each of these points and flip them over the x-axis, I'm going to get, well, I'll get 0 staying at 0. I'll get this set of points. Now, each one of these points is going left 2, down 3. So I got new points here, 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 and here. Well, actually, I think I whiffed on one of them. This one should have been one lower. There we go. All right. So then I'm going to draw a new curve starting at the leftmost point and going through the others best I can. Put a little arrow on it and then label it. You just label it h of x. That's how we did it during the lesson, and that's fine as long as there's some indication of what the equation is. H of x is perfectly fine. All right. If you want to write h of x equals all the other stuff, that's great, but not necessary. Sorry, I'm just cranking out some attendance here. All right, but yeah, just knowing that that parent function goes a long way. And later on, when we talk about cube root functions, you'll see it's the same idea. In fact, anytime we talk about the standard form of an equation, it's really that. If you know some characteristics about the parent function, all you need to know is what role the a, h, and k values play on the transformed function as opposed to the original. All right. Then the last one, last but not least, we're pulling an equation from the graph. All right, so we're starting off the same way here, where we're going to look at the square root of x as an equation, graphed. So 0, 0, 1, 1, 4, 2, 9, 3. All right, that's my parent function. Okay, kind of missed, but okay, doing that again. All right, so that's f of x is equal to the square root of x. I just want to think about how this became this. All right, well, it looks like it was flipped over first and foremost, so that's good to know. All right, so I know I have a negative a value, but you kind of look at it and say, oh, well, let's just do that. Let's flip it over and see where it would go. If I flipped each of these points over the x-axis, this is where it would end up. All right, so that's not quite where I need it to be. So instead of having a point at the origin, that point needed to get over here somehow. So that looks like a shift. All right, but the shape of it looks a little different. All right, so I also have to think about not only the shape orientation, but I got to think about whether or not there's a stretch. These points over here look much further away from the x-axis than these points. All right, so I'm suspecting that there's a stretch involved. But let's take care of the h and k values first. To get this point to this point, it looks like I'd have to have an h value of 2 and a k value of -1. All right, so that's what I can do. I can take my points and move them over to those locations. All right, so shift right over, down 1. Okay, so it looks like it's starting to line up a little bit, but not quite. I need this point to go here using some kind of stretch. Oh, that's lovely. Well, about to end this anyway. So you got to think about how you can accomplish that. Well, I don't want to shift it. If I shift this point down 1 unit, it's going to shift everything else down 1 unit. All right, so that's not going to work. So that's where the stretch comes into play. You think about the difference between where this point is in relation to that first coordinate. It's 1 unit away. I want it to be 2 units away. All right, so what I would do is I'd create a stretch factor of 2 and see if that gets the job done. All right, so I know the A value had to be negative because there was a reflection. I suspect it's negative 2. So I think my function here, f of x, is going to be negative 2, the square root of x minus 2, minus 1. All right. So we'll check it in the calculator and see. I gotta see if there's a way I can charge this with that. Oh, you know what? I can do it this way. So in the calculator, wherever I put it, oh, there it is. I would type in this function, this new function. Let's see. I'll cover this for a second, then I'll bring it back. All right, so y equals, let me get rid of this, negative 2, the square root key, same square root key you always use, so second x squared, then x minus 2, hit the right arrow, minus 1. All right, 2 ways to handle it. One would be to look at the picture, just a quick eyeball. So zoom 6. So you take a look at this graph and compare it to the one that's on paper and see if it looks roughly the same. Maybe it does, maybe it doesn't. All right. Sometimes it's like, well, I think it kind of looks okay, but I'm not 100% sure based off scaling. That's when you go into the table of values. So second graph, see a lot of error because you're not going to have negatives as a result of, well, actually, you're not going to be able to take the square root of a negative number. So we ignore all of those possible outcomes. But you could also, if you're just taking the square root of any kind of variable value, the result could never be negative. So that's just specific to a parent function. Right? Doesn't really apply in this case, but that's also another reason why you might get something that doesn't lead to an outcome. So 2, negative 1, that's the first coordinate that exists. Looking at my graph here, over 2, down 1, that's a point on the graph. 3, negative 3, 3, negative 3, yep. Decimal values, okay. How about 6, negative 5? 1, 2, 3, 4, 5. If that little thing wasn't in the way, it would show up. So 6, negative 5 is also a point on the graph. So we're verifying, just kind of going by the clean ones. 11, negative 7 is off the grid. But the ones that are clean and obvious, they verify, they check out. You could also verify using the decimal ones. It's just a little iffier. So for example, 4, negative 3.8. That could be negative 3.8. Negative 3.8 units down, 3.8 units down from the x-axis, right? So it checks out. So we had a suspicion, and we verified our suspicion using the calculator, right? But the first thing I always do when it comes to writing the equation is I take into account whether or not the a value is positive or negative, right? If it's above the axis, it should be positive. If it's below, it should be negative, right? Then I get into shifting and trying to align it as closely as possible, and then I account for stretch or shrink. Right. Going back to number 5, so we're kind of going reverse order here. If you just wanted to create the graph, just type it in. X plus 2, close it up, minus 3. Again, you can look at the picture, zoom 6. It'll give you a general sense of what the graph ought to look like. But if you want to get points on paper, second graph brings you to the table. You see a bunch of errors. You want the first point after the errors stop. All right? So negative 2, negative 3, negative 1, negative 4. Ignore the disgusting decimals. 2, negative 5. 7, negative 6. And if you find any more, that's great, but the next one falls off the grid. All right? So just take the clean ones. If you want to plot the funky decimals, that's fine, but that's going to be overkill. We'll just put it that way. Right. And again, because I'm not asking, I mean, I made the statements of the reflections and the translations and all that, but you didn't need to. All right. For the piecewise functions, pulling it from a graph, it's really not much a calculator is going to help you with there. So it's really more for this one. And honestly, even for something like this, all you would be using the calculator for, if I type in 5x minus 3, second graph, I would just be looking, I made a table going from 0 to 1. I would just be grabbing 0 and 1, -3, +2. Then I would do the same thing for g of x equals 4. So I would type in just a 4. And do that from +1 to 4. So just these values, that would make up my table. You know, so this is probably one of the instances where it takes more time to type it into the calculator than it does to do it by hand. So you're probably better off just doing it by hand. But, you know, if you don't want to take any chances, maybe you do it both ways. All right, the last one is going from 4 on to infinity. So start your table at 4. Grab some points. You would need, I would only take the clean ones, plot them, and throw an arrow on at the end. All right. And then the absolute value graphs, really, I mean, they're both kind of the same idea. So y equals, if I want to graph, I'll just do number 1. -3, we hit alpha window, brings up the absolute value function, ABS. Alpha window option 1, type in x minus 2 plus 2. All right, again, you can look at the picture, zoom 6, tells you a little something, but if you really want the good stuff, you go into the table, so second graph. Now, you want points surrounding the vertex. All right, so I hunt around until I have symmetry in the y column. All right, you see here I have 2, 2. That's my vertex. These are the relevant points. Top matches with bottom, second from the top, second with bottom, and so on. These are the points I want to use to create my graph. Once I identify these points, pop them down on paper, make the appropriately shaped graph, and you got what you need. All right. So that's really it for the absolute value functions. All right, so there's really not much to it there. Okay. And that was it. So tomorrow's quiz is really just going to be this.